So far, we've been working in equilibrium in 2D with our rigid bodies, but we can also work in a 3D space. Now, the thing with this is that there are now 6 degrees of freedom when we work in a 3D space. So we have, in our 3D space, we have our force in the Z direction, force in the X direction, force in the Y direction, and then we also have these moments about each of these axes, right? So this would be the moment about the y-axis. We also have a moment about the z-axis and a moment about the x-axis. And these usually assume right-hand rule, direction of rotation, so that your thumb points in the direction of the axis, and then the way your hand curls indicates which way the positive moment is going. So that's the sign convention we use. Use the sign convention of the right-hand rule when you're taking these moments. So we have these 6 unknowns typically. You need 6 separate equations for these 6 unknowns. So our 6 equilibrium equations are now going to be the moment of each axis being 0, as well as the 3 forces all being 0. Which 6 reactions sounds like a lot, right? It's it's a lot of reactions. It's a lot going on here. 6 separate equations to solve and find things for. But in 3D, you need 6 support reactions for something to be considered stable. So in order to calculate these, we're going to be going through all of these 6 equations for all of the problems we're going to encounter. Before we do an example, let's talk about some of the support reactions that you're most likely to see. So you might see something like a smooth surface support, or a rocker or a roller, and these just have single forces on them, basically like a normal force supporting them in whatever way it's contacting the surface. So you can think of these for a smooth surface support, or a roller or a rocker, something like that. It's basically just a normal force is what's supporting it, keeping it from falling through the floor. You'll also still see the pinned connections that we saw in 2D. They'll usually look something like this, with these flat plates on the side maybe, and you have a pin or a rod going through them. And these are going to be locked in the, I want to call them up and down directions, but it's not quite right. It's whatever way this thing is oriented. So in this example, it could be like Fy and Fz, but could still move in the way that this rod moves. So there's still a degree of freedom on this third side, but it works just like a pin where there are 2 support reactions that are just forces, no moment support reactions generally on these types of things. If this is the only thing there, it might have other moment reactions, but if it's in a part of a larger system, it just has these 2 support reactions, which is usually how you'll see it, as a part of a larger system. It's a little confusing to know when there are moments and when there aren't, but your book does have this table of more assortment of things than we're going to talk about here, but an assortment of which ones, what type of thing is it, which forces do you use, and note when the moments may or may not be acting. For example, they say note moments are not applied if the body is supported elsewhere. And so many of them are like this. Here I'm assuming the body is supported elsewhere. There are other supports and reactions and components, so there are only these 2 forces. Now the main new one that you're going to encounter is a ball and socket. Oops. Ball and socket. And a ball and socket usually looks something like some support with a ball in it, right? So there's some little cup that's supporting a ball that is attached to a rod or something like that. And this support reaction applies 3 forces, right? So it supports in the X, Y, and Z directions, but it allows for freedom of rotation, freedom of movement, so there's no moment support reaction here. But it constricts in all 3 force directions, X, Y, and Z. And then finally, the most common one you'll also see in here is a fixed support. So just like how we had in 2D when we had a fixed support, it constrained the 2 forces in the moment, so it constrained our 3 equations, right? This is going to constrict all 6 directions of movement. So again, it can't move in the Z, Y, or X. All of these it prevents movement in, but also in their moments. Right, so there is a support reaction moment also in the X, Y, and Z directions. So before we get into actually solving these things, let's again, as we did in 2D, take a look at how we set up free body diagrams for these systems in 3D. In this example, we're going to draw a free body diagram for the system that starts at point A on the x-axis, goes to the origin, and then turns 90 degrees following the y-axis through point B, and then makes another turn 90 degrees up in the z direction. And we notice it has 2 applied, well, 1 applied moment and 1 applied force. It has an applied moment of 45 Newton meters on the x-axis, and then 500 newtons pointing down in the negative z direction. So when we're drawing our free body diagram for this, what we're looking for are where are the support and reactions, and how are they reacting? What directions are we assuming they're reacting? And we can see at A, B, and C here, we have pinned connections at each of these locations. So for a pinned connection, I'm going to have 2 directional supports, right? And it's not going to be on the axis that it is on, right? So when I draw this free body diagram, I'm just going to draw, let me make that thicker. I'm just going to draw the general shape of this thing again. I'm not including the pins, I'm just making the shape of it. And I have this 45 Newton meter moment, this 500 newtons, and then I have my support reaction. So at A, I don't have a support reaction acting in the x-axis, in the x direction, because it's on the x-axis, right? It's oriented so that the pin going through it is going through the x-axis. So I have supports in the y and z directions. So these are my support reactions for a 3D pin. It's going to be the y component of A and the z component of A, but no support in the x direction. And I've drawn these kind of randomly. It doesn't matter if they're pointing inwards or outwards, or if my AZ, instead of being here, was located here, right? They're in the same direction. They're on the same point. And that's what's most important, is that this is really, it's just a visualization tool for us to set up our equilibrium equations. Those are my A forces, and it's going to be the same for the pins at B and C. But I notice my B is rotated so that now my pin is going through the y-axis. So at B here, I'm going to have an X support reaction and not one in the y direction. But again, still have one in the z direction. So I have a BX and a BZ support reactions at point B. that pin, even though it's in the middle of the system, it's in the middle of the rod there, still has support reactions acting on the system. And then finally I have point C. It's kind of on the ceiling there, and so it's going to have support reactions from this way and this way, the X and Y directions. Right, so this I'm going to call CY, and this one I'll call CX. And this would be my free body diagram. We could add our lengths in here if we were given lengths for this. We could also choose to not add them just because it could get really cluttered and messy to read. But this is our complete full body diagram for this problem. Let's take a look at another one. Now in this example, I have 2 connection points and 2 applied forces. So my applied forces we'll ignore for now in setting up the free body diagram, but let's take a look at those 2 supports. So at the top where I have this little cross-hatched area, that's usually representative of a fixed support. So it's kind of fixed up on the ceiling. Anytime you see that hatching or kind of a shading, it's a fixed support at my top there. And then if I look down at the very bottom, I have a pinned support. So when I keep this in mind, I'm actually going to have 8 reactional forces here, because a fixed support has all six directions supported, where a pinned connection has just 2. So when I draw my free body diagram for this, I'm going to draw my little zigzag. Go ahead and put on my applied forces. I have this 400 newtons here, and this 200 newtons down in the negative z direction. And now I'll take a look at my supports. So if I look at the very bottom, at that pinned connection, I'm not going to have one in the x direction, but I'm going to have supports in the z and y directions. So here I'm going to have, let's give this a name. Let's call this point A, and we'll call the ceiling here point B. So here I have an AY support, right? It's parallel to this y-axis, right? And a support in the y direction and a support in the z direction. Again, doesn't matter which way you assume these arrows go, the math will work out to tell you whether you were right or wrong in your prediction. And that's it for our point A, right? Point A just has the 2 support reactions, and then point B, being a fixed point, is going to have 6, right? 6. Everywhere is supported, everything is firm, it cannot move in any direction, has no freedom of give in any direction. So our FZ, FY, FX, as well as those moments. I'll do in a lighter color just to see better. So moment reaction in the y direction, moment reaction in the z direction, and a moment reaction in the x direction. So again, I've got 8 unknowns here. This would be indeterminate. We wouldn't be able to solve it because there are more reactions than we have equations, but this would be how we would set up the free body diagram for this. Let's take a look at one final free body diagram here. Here I have this plate that is supported at points A, B, and C, and each of these supports are a little bit different. So at A, we have this little ball. So this little ball allows movement in all directions except one. It acts directly up as like a normal force onto this plate. So of course my first step is drawing this plate as my free body diagram, and I'm going to go ahead and add in these applied forces that I'm seeing. So this is the 200 Newton meter moment. Here is a 300 Newton force acting downwards. And now I'll look at my support reactions. So at A, it allows movement in all the directions except up in this Z direction as like a normal force. I'm going to call this force at A. Force at A acting upwards on the plate. Then I'll move on to looking at force at B. Now the difference between A and B is that A is just this ball that's allowed to move and rotate wherever, whereas in B, it's stuck inside this little cup. It's a ball and socket connection. So this means that my X, Y, and Z directions are all fixed here at point B. So in all directions here, my Fx, Fz, and Fy, if I make an assumption on direction here, it's fixed in all three directions for point B. And then finally, my last connection is at point C. But be very careful here, because you might be tempted to say, okay, I see that this rod is connected to the ceiling, so it's a fixed connection. But actually the body that we're interested in is the plate, right? And this is just a single rope that's connected to the ceiling. You can almost think of the rope as like a two-force member, where it has this force on the ceiling and a force on the plate. So the only force acting at point C here is the tension force from the rope. It's not locked in any other direction. It's a rope. It can swing around if it needs to. The only force acting here is the tension T in that rope. And then there's one last thing about a plate problem or any of these problems that may trip you up if it's part of your problem statement. And that is, when you have a plate like this, oftentimes we do account for the weight of the plate. So the weight is kind of like a distributed load acting through the whole plate, and your weight acts through the centroid of that shape. So here we might also have a weight in the centroid of the shape, W. And usually this would be given to you, or you might be asked to find the weight of a plate. But usually it'll say a plate has a weight of this amount, or maybe it gives you a density, so you have to calculate the weight using the density and the area of the plate. But be very careful, because we do want to account for that. It does contribute to the load. It is a force that contributes to the system. So not only do we have those 5 reaction forces, we also have the weight of the plate.